I'm gonna, for the first part of this talk, I'm gonna try to give a bunch of background on K-theory in general, K-theory of commutative rings in particular, some of the history, and some of the sort of first steps towards what I'm going to discuss. So if there are any questions at all, please don't hesitate to chime in. So I'm going to assume that Z mod P to the N is a known quantity. So this means the commutative ring of integers modulo this power P to the N. So it's a finite commutative ring, but if N is more than 1, it has nilpotent elements. And so it's not a field. It's not the field with P to the N elements, of course. And that means that it's, invariants of it are trickier to compute than they would be of fields. And that's really at the heart of the story I'm gonna tell today. So, okay, so this is all under part 1, which is going to be background. And let me just start us off. The first background that I'd better tell you about is, that's the same color. Not what I meant to do. My bad. What is the definition of algebraic K-theory? So first of all, let me just explain something that one can do. So let's suppose I have M. This is a commutative monoid. So that means that it has an operation plus, and it has an element 0, and this 0 is an additive identity, and it's associative, but it possibly doesn't have inverse. There are possibly not negatives of elements, so possibly no additive inverses. So that's this is just a basic algebraic structure. And what I can do, one thing I can do if I want to just force additive inverses is I can group complete. I'll call this M group. So this is the group completion. And this is just sort of a universal object where you force M to have inverses. So you add inverses in a formal way. I'm an algebraist and a category theorist. One way I like to think about this is that I have the category of abelian groups, and I have the category of commutative monoids. And there's a forgetful functor. I can forget that an abelian group has inverses and just view it as a commutative monoid. This forgetful functor has a left adjoint, which is group completion. Okay, so in particular, that means that M has a universal property, namely to give a map from M to an abelian group A is the same as to give a map from the group. So to give a map of commutative monoids is the same as to give a map of abelian groups. Okay, that's what it means to be adjoint. So this is a totally universal construction. Now, why might you care about something like this? Well, I don't know if in your life you've ever used negative numbers. I've done it once or twice. And so the standard example is I can take n to be this is 0, 1. We don't have to fight about whether 0 is in the natural numbers or not. I just mean this is what I mean by this symbol, and I view this with the addition of integers. And I want to group complete, and when I do, I get the abelian group of integers. Okay, so maybe I wanted to do some double entry bookkeeping, and so I needed minus signs. So anyway, so this is just a simple example of an operation you can do to a simple algebraic object. And about 70 years ago or so, 60 or 70 years ago, this was applied in the context of algebraic geometry by Grothendieck in his formulation of the Grothendieck-Riemann-Roch theorem, which is about, at the end of the day, it's about computing various Euler characteristics in the context of algebraic geometry. Well, what are those Euler characteristics? Well, those Euler characteristics are various alternating sums of dimensions. And those alternating sums, you need the minus signs in order to be able to do that. Okay, so to get a general formulation of this Euler characteristic, Grothendieck was led to introduce K-theory into the context of algebraic geometry. And so what can you do? So another sort of example is you can do the following, or construction. Let's suppose now, for simplicity, R is a commutative ring with, associative with one, et cetera, et cetera. So from R, I can cook up the following category, which is, it's just this category of projective R modules, which are of finite rank. I'll just say FP, finitely presented. So this contains all finite sums R to the n and retracts of those. Okay, because those are what the projective ones are. And it's a full, I'm viewing this as a full subcategory of the abelian category of R modules. And this has one sort of crucial feature is that it has direct sums. So it has some kind of operation. If I have two projective modules, I can take their sum. Okay. And so what that does is that I get a monoid from R by taking proj R, finally presented, modulo isomorphism. This is now a set, right? Because there's small amount of these. So modding out by isomorphism produces a set, but direct sum preserves isomorphism. So this still has an operation on it called direct sum. And this is a monoid. And Grothendieck's definition of K0 of R is you take this monoid and you group complete it. Oh, I'll write it like this. Take that monoid and group complete it. So let me give a couple. We're about notes here. Let me give a few examples of this process. Oh, okay. So maybe that's. Let me come to examples in a second. So that's the definition of K0. And if K0 was just all there was, there wouldn't be much in this talk. But there's not, and people figured out, basically the story was as follows. Very quickly after this kind of definition, Antieau and Hirzebruch extended it to topological spaces, and they proved a bunch of things about topological K-theory. I'll come back to that in a second. And that really that suggested, and other sort of calculations suggested that there should be higher K groups. This should just be the first of an infinite sequence of groups that we're going to abelian groups that we're going to attach to this commutative ring. So let me just go ahead and define what for me will be algebraic K-theory for the purposes of this talk. And it's going to be the same thing. So this group completion here has to do with this formal adjunction procedure. And the idea now is we're going to view ourselves as having been a little too brutal when we made this definition. We don't really want to forget isomorphisms. There are interesting automorphisms of even a single abelian group. For example, I'm going to claim that GLNZ is kind of interesting. That's abelian group automorphisms from Zn to itself. And so that suggests that maybe we don't want to collapse all of those to a point, but maybe we want to do some operation that remembers something about those automorphisms. And so, so here's what we do. So instead of, right, so instead of this brutal procedure where we forget all of the isomorph, where we quotient out by all of the isomorphisms to get a set, what I'm going to do is look at proj R finally presented. But now, instead of taking this set of isomorphism classes, I'm going to write equivalence here. Okay, so what this means, this is a subcategory. Maybe I'll write, I don't want to say that. This is like, this is the subcategory with the same objects, but only isomorphisms. So in proj finally presented, I can have the 0 map, or I can have a map which is multiplication by 7, et cetera, et cetera. In this subcategory, I don't have anything. Okay, I just have equivalences. So it's more than nothing. So I in particular remember the full action of GLNZ on the free abelian group on n elements. And so this is a category, but all of its maps are equivalences. So this is an example of a groupoid. It's a category where all arrows are equivalences. Okay, and so that's something that is interesting. Well, groupoids, basically, you can think of a groupoid as a special type of space. Spaces, in some sense, are infinity groupoids. So what I want to do is I just want to think of this as a space. And what it is it's a disjoint union as a topological space. It's homotopy equivalent to a disjoint union where you do range over iso classes in proj R finally presented, and then you take the classifying space of the automorphism group of R of P. So it's as a space, it's a bunch of disjoint components, and each component is a k-pi1 space. It's a k-pi1 space, i.e. as a path-connected space with only a single homotopy group, and that group is this automorphism group, as pi1. So as a sort of side example here, because every finite rank projective module over the integers is free, if we do this for Z itself, oops, iso, what's my notation? Equivalence. Then I get the big disjoint union of B, G, L, and Z. Okay. And the crucial observation is that this is not just any space, but it's an H space, because there's still a direct sum operation. Okay, so I still have a direct sum operation. And it makes it into an H space. So, okay, so now what I'm going to do is group complete, but now I'm not going to group complete in the world of sets. I'm going to group complete in the world of spaces, because this is a space. This is like a monoid object in topological spaces. However, to do that really rigorously, one has to either use some theory of operads or some theory of infinity categories. So there's going to be a little bit of magic under the hood, but I can mimic this construction up here, and I'll say the following. I'll say I have C mon infinity and ab infinity for the purposes of this talk. Okay, so CMON infinity, these are sort of you know, I'll put it in quotes, these are commutative monoids in spaces. And if you want me to put it not in quotes, what they're really like is E infinity spaces. And these are going to be the same things, but here we're going to assume, so if you have a commutative monoid in spaces, then pi 0, which is the set of path components, it's a monoid structure. And so ab infinity will be those where the monoid pi 0 is actually a group. So it's a full subcategory. I look at all of these E infinity spaces where pi 0 is a group. So these are called group-like E infinity spaces. And there's a left adjoint, and I'll just still call that group completion. It exists for formal reasons, and it just formally takes the sort of universal space where you've now added inverses to that, to all of the elements in pi 0. Okay, and now the connective key theory of a ring R this is, I take this, I take proj R finally presented, and this is an E infinity space, and I group complete it. And Ki connective R is pi I of this, the resulting space. I'm going to be a little sloppy in this talk. Oftentimes, I'll also view this as a spectrum, which is some kind of higher analog of a chain complex. And then these pi i's from that perspective are some sorts of analogs of the homology of a chain complex. But let me not go into any detail. Okay. So that's a definition. That's a rigorous definition of higher K theory. It's perhaps the shortest, at least if you grant me this notion of an E infinity space. But now let's forget about that and let's go to some examples, and see what's going on. And feel free to interrupt if there are any questions. So, well, the first point is that we haven't actually changed. So maybe I'll even just write this KIR equals this. So the first thing to note is it's the fact that if I compute K0R this way, it agrees with the definition I gave up here. So we haven't changed K0. That's a plus. Now we have possibly higher homotopy groups. And now, yeah, so let me give some examples. So if K is a local ring or PID, then K0 is Z. So this includes the case of fields, includes the integers. It includes any commutative local ring. Okay. What is that saying? That's really just saying that in those cases, all finite rank projective modules are free. So what are we doing? We're just group completing the monoid n, and we already saw that the group completion of n is Z. But there are other cases which are not so far from that. In general, if I take K0 of a ring, OK, so this is a ring of integers in a number field. then this is isomorphic to Z plus the class group of K. The class group of K is also just the Picard group of the ring of integers of K. And roughly speaking, this isomorphism, what does it do? Well, it takes the rank and the determinant of a given finite rank projective module. And that turns out to give this isomorphism. Okay. And so this is kind of interesting. So, for example, one case is you can take Z square root minus 5. That's the ring of integers in the field where you would join a square root of minus 5 to the rational numbers. And it turns out that this is not a principal ideal domain. There's a prime with two factorizations. I forget off the top of my head which prime it is, but okay, we can figure that out, but it doesn't really matter. What turns out is that the class group of K is Z mod 2. And so that implies that K0 of this particular ring, square root minus 5, is isomorphic to Z plus Z mod 2. And again, yes.
I think that's 6, right? 6 equals 2 times 3 and equals 1 plus going of
Yeah.
1, 5. 1
Yeah,
minus.
1 plus square root minus 5 and 1 minus square root minus 5.
Yeah.
Yeah, looks good. Thank you. Okay, so unique factorization. Yeah, so well, anyways, so it's not a prime ideal. It's not a principal ideal domain. Thanks. So this is the sort of thing that can happen in K0. So for the most of the rings that we're going to care about, K0 is known. It's going to be isomorphic to the ring to Z, and that's not going to give us a lot of information. So what about other things? So if I have K1 of a local ring R, then this is isomorphic to the units in R. That's kind of nice. That means this is an interesting invariant. I'm picking out the group of units in R that's getting spit out by this construction. And D, let me give a theorem of Matsumoto. He computed K2 of a field, K. And it's isomorphic to the tensor product of the units with themselves over Z. It's kind of weird. The units are an abelian group, so I can take the tensor product over Z, even though it looks like a strange thing to do. I take this and I mod out by certain elements, namely the tensors of the form a tensor 1 minus A, for A not being 0 or 1. So that's random, but it turns out to be very closely related to a lot of deep work in algebraic K theory. And let me let me give a couple, just 2 more examples. This was a theorem due to Matsumoto. And then this theorem is due to Merkuriev and Suslin. And well, it computes K2 of K modulo L when L is invertible in K. So if you like, you can think of K as having characteristic 0. So then this would work for any prime L. And this is actually always isomorphic to an Antieau cohomology group, spec K, with coefficients in this second twist of mu L. And this is isomorphic in the special case that K contains a primitive Lth root of unity to the L torsion in the Brouwer group. Okay, So that's kind of fun. We're getting from, I think what you'll agree is a pretty crazy abstract garbage definition, some interesting invariants of our rings, okay, sort of for free. All we did was a universal property where we universally made this E infinity space into a group like E infinity space. It's not even clear, this E infinity space that we start with, let me just emphasize this. Right. This E infinity space that we start with has no homotopy groups above pi1. It's disconnected. It has no homotopy groups above pi1. When we group complete it in this world of topological spaces, there's typically infinitely many homotopy groups that are non-zero. So this is a really complicated topological operation that's happening. And I think that's, evidenced by the fact that we get out interesting field theoretic invariants. Let me mention one more example for the moment, which is if I take a regular Noetherian ring, so this is an abelian group, this K0, and so I can in particular rationalize this abelian group, just tensor it with Q. And then this is isomorphic to a direct sum over I of the rational Chow groups of R, which these are defined in terms of cycles, algebraic cycles on the scheme spec R. So even for K0, we get out some very important bits of information from K0. So okay. Okay, so that's a little bit of background. Now let me say a little bit more about sort of the lay of the land in algebraic K-theory. So the next thing I want to say, I'm skipping around here. Well, okay, let me. Okay, this is like an important theme of the talk, so let me just go through it rapidly. C, let me just mention the Antieau-Hertzebruch spectral sequence. Spectral sequence. So the idea is that, right, so I can take a topological space X, and I can define KU upper 0 of X, which is, this is the same construction. This is now the group completion of the monoid of isoclasses of complex vector bundles on this topological space X. The thing I can do. And for example, KU0 of a point is just isomorphic to 0, because again, this is the group completion of, there's only a single topological vector bundle on the point of any given dimension. And so this is again the group completion of the natural numbers. And kind of what turns out to be is that this is also isomorphic, or sorry, this is isomorphic to homotopy classes of maps from X into Z cross the classifying space of the infinite unitary group, at least for X reasonable, like paracompact Hausdorff or something like that, but certainly any CW complex is okay. And then there's an amazing phenomenon called Bott periodicity. And what does it say? So it take the loop space of Z cross BU. Well, of course, you have to fix a base point. So this produces for you the infinite unitary group. But now, okay, so this first thing is not crazy. This would be true for any classifying space. But now take loops of U. And Bott periodicity tells you that this is actually equivalent to Z cross BU again. So you can keep hitting loops, and you just go back and forth between the same two spaces. So these assemble into a spectrum, Z cross BU, U, Z cross BU. And, you know, loops of this is this, loops of this is this, and so on and so forth. And then the topological KU cohomology of a space X is pi minus R of the function spectrum from X to KU. And so, right, if I do this to a point, this turns out to give a graded ring, and I get Z adjoin beta plus or minus 1, where the degree of beta is is plus 2 homologically. So what's the point of all of this? Well, the point is that Antieau and Herzebruck found a spectral sequence that computes the K groups. Okay, so they gave a spectral sequence, and the spectral sequence looks like as follows. The E2 page is HS minus T X Z, and it converges to KUS plus TX. This is a reindexing of the usual spectral sequence. Let me just remark that the differentials have degree R1 minus R here. And no. This is not the usual indexing. There's a bunch of zeros in the usual indexing, because a bunch of the homotopy groups are 0, all of the odd ones. And so this just speeds things up. And so it skips all of the odd differentials in the usual spectral sequence. So that's all the reindexing is doing. So what you see is on the main diagonal, when you draw this out, you get H0, 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 and so forth. And then one below the main diagonal, you get H1, 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 I guess, and so forth. Okay. So just as an example, and then how did the differentials look? You know, the differentials, like roughly speaking, go this way. And so you can easily use the spectral sequence, although this is, you know, not the best way to prove this. It's probably somewhat circular, but you can compute that KU0 of S2. So for S2, there's only 2 degrees of cohomology. So you'll have this line and you'll have this line corresponding to H2. And what you can prove is that then this collapses and you get Z plus Z. So that's interesting. That tells you that there's a non-trivial topological vector bundle on S2. Well, what is it? For example, the tangent bundle is 1, and its non-triviality has to do with the fact that there's nowhere non-vanishing continuous vector bundle, a vector field on all of S2, which is often called the sort of hairy ball theorem, right? Any way you comb your hair, there will be a sort of singularity. So you can see this. A lot of the history of algebraic K-theory is bound up in the search for a spectral sequence like this for algebraic K-theory. Okay, and so that's going to be you know, what goes into the work I'm going to talk about. Okay, so D. what are the hints of this motivic filtration? So this is sort of prehistory, if you will. And the first is a theorem of Quillen, 1972, and this is the first full calculation of the K-theory of any commutative ring. So you look at K-theory of the finite field with Q elements. This is clearly should be one of the first examples one should try to compute, and that's what Quillen did. And well, the point is that this space, BU, BU, this classifying space of the infinite unitary group, it has operations on it called Adams operations. And those are denoted psi upper K for various K, but the one that matters here is Q. And if I force psi Q to be the identity, i.e. I take the fiber, then I get an equivalence. At least this doesn't quite get K0, so I get sort of all of the higher K groups this way. And this spits out an actual calculation. So the point is that psi q acts as q to the I on pi 2I BU, which is isomorphic to Z for I at least one. So the long exact sequence from this fibration tells you that, well, so in particular, I get Z, in degree 2I, I got Z, and I get 1 minus Q to the I. Well, that maps injectively. And so I see that this is 0 onto K2I minus 1 of FQ. And so what I get is a table for the homotopy groups of FQ. K0 is Z. K2I of FQ is 0 for I positive. And K2I minus 1 FQ is Z mod Q to the I minus 1. Okay. That's a complete calculation. And I think people were thinking that, this does sort of suggest that there's a connection between algebraic K-theory and some sort of a Tia-Hertzberg spectral sequence, because you have this direct connection between these sort of, this two periodic cohomology theory here and this. And indeed that turns out to be the case. Let me just say, right, so then, Quillen conjectured, well, I guess I'll call it Quillen-Lichtenbaum conjectures. This was in Quillen's ICM address in 1974. And he conjectured that there should be a spectral sequence of the form it's kind of like the Atiyah-Hertzberg spectral sequence, except I forgot to index it so that a bunch of things don't vanish. But okay, converging to K minus P minus Q. It's a little bit more visible. Of R coefficients in ZL. And this convergence should be, at least for if my minus P minus Q is more than 1 plus D. So this is for R regular Noetherian ring of curl dimension D. So, he had done some calculations, and there were sort of conjectures. Lichtenbaum had thought about special values of zeta functions, and together with these calculations in low degrees, they cooked up a guess for how the higher algebraic K-theory groups should look for the integers. And there's a little bit of haze here, and that haze basically is not, I'm just going to ignore that for the rest of the talk. This will roughly speaking be the motivic filtration, but the haze has to do with the fact that we have a tall cohomology here. And really what that means is that this should converge to a tall K theory, which is it's a tall sheafification. And that turns out by a major theorem not to change too much. So this Quilling-Lichtenbaum conjecture is actually a theorem now due to Rost and Voevodsky, and many other people putting in work on the way. But so that means that the higher K groups have to do with a tall cohomology, and a tall cohomology is something that's supposed to be interesting, but it's computable. That's the point. Oh, and this L had better be invertible in R. So now let me just tell you very briefly about fracture. And it's a philosophy, classical philosophy, which just says that you can, it goes back to class field theory, that you can glue any abelian group out of rational and p-adic information. Okay, so I can take M and I can rationalize it. The other thing I could do is I could profinite complete it, and then I could rationalize the profinite completion. And this is a pullback square. Maybe to make this completely rigorous, you want to do this all in the derived category of abelian groups. But in particular, this is a product over all primes P of the P completions, the p-adic completions, where I put the p-adic topology on F. And so, an important approach to K theory that I just wanted to mention, and is going on in the background of a lot of this is, K theory of R is very difficult to understand. And so one tries to break it up into pieces. You first try to understand KR with rational coefficients. Maybe you try to understand KR with L completed coefficients. And then when L is invertible, and then maybe you need to consider the p-adic completion where P is not invertible. And if you could understand K theory at all these different spots, then you could try to glue them together and understand K theory globally. Okay, so that's a strategy for understanding K theory. And let me just try to identify what the issues are. So rational K theory, we already saw, has to do with Chow groups, even in degree 0. So this rational K theory has to do with cycle theory. And we know this is hard. Okay. So it turns out nowadays, this is actually the hardest part of algebraic K theory, and I have nothing new to say about this. Although for the rings that I'm going to talk about, it's not so relevant. This has to do with a tall cohomology, and after the very deep work of people like Suslin, Voevodsky, Friedlander, Rost, Morel, et cetera, this part can basically be viewed as boiling down to the computation of atal cohomology groups. Now, the computation of atal cohomology groups is itself hard, but at least, that's something people have spent a lot of time working on. Okay, so that's, from that perspective, it's known up to you just have to compute the atal cohomology. That leaves the p-adic part, and the p-adic part is has perhaps been the most mysterious up to now, but let me just say that this has to do with trace methods and p-adic cohomology theories. And, we're in the early days of this, again, maybe not so early, but, one of the nice things, so atal cohomology, one of its main defects is that there aren't good cycles for it. The way that there are for de Rham cohomology in characteristic 0, if I have a complex manifold, a cohomology class, then there's some actual differential form that represents that cohomology class. And so I can take that differential form and study it and use it. Atal cohomology does not have that feature. But it turns out that these p-adic cohomology theories, at the end of the day, are built out of differential forms theory. And that makes them somewhat amenable to computation. And as I'll say in a bit, in fact, machine computation. So let me, I guess we're to have a break in a moment. Yes?
Yeah, never mind.
Okay. So let me just show one quick thing, and then we'll take a break. It'll be a good spot. So this is taken from Weibel's survey on the algebraic K-groups in the Handbook of Algebraic K-Theory. And it's a picture of the first few K-groups of all of the integers. And you see these are interesting numbers. And not all of them are known. So basically, everything is known except when in the two cases where the degree is congruent to 0 modulo 4. Okay. And this table, sorry, I can't point here, but this table down here says that, you know, for example, 8a plus 1 at z plus z mod 2, 8a plus 5 z, and then there's some invariants which are basically computable, these c and w numbers. So you can view all of those as known, and then there's just this problem for computing it for 8a and 8a plus 4. And this problem, what does it have to do with? Well, going back to here, it has to do with computing the étale cohomology of the numbers of the ring of Q in the end. One reduces it to computing the étale cohomology of Q. And so it turns out that there's just open problems in the étale cohomology of Q. And the conjecture is that those 8a, right, sorry, that K4a of z is 0 for all a at least 1. And this is true if and only if a crazy Van Diver's conjecture is true. Van Diver's conjecture says that you take Q, you would join a primitive p root of unity, and then you take plus. This plus means you take the maximal real subfield. So this field contains a largest field, which can be embedded in the real numbers. And you take the class group of this field, and then you take the number of elements in the class group, and the conjecture says that P does not divide this for any prime P. Okay, or for all P. So you look at all prime numbers P, you look at this maximal real subfield of the P cyclotomic extension, take a look at the class group of that, and the guess that P does not divide the order of that. So I say this just to give some sense that, like, K-theory is an ultra deep invariant, despite our seemingly very, I don't know, ad hoc definition. We take something and we group complete it, and that's supposed to be interesting. Okay, let's take a break now.